Hi, everyone. Welcome to this Tech Talk. Really glad everyone could make it. I'm here to introduce Matt Godbolt. Matt Godbolt is a C++ developer who loves looking under the hood of compilers, operating systems, and silicon. By day, he writes software for finance, like many of us here. By night, he emulates vintage computers and maintains Compiler Explorer. Well, Compiler Explorer is the official name, but everybody knows it as Godbolt. So naturally, when someone set up the Jane Street internal instance, they named it Godbolt, making Matt the first external speaker who already has an internal domain name named after him. Please join me in welcoming Matt Godbolt.
Thank you, Jasper. Well, thank you for having me. This is fantastic. I'm looking forward to talking to you about the kind of things that I love digging into. So this is microarchitecture, what happens beneath, which is not my best title. So yeah, as Jasper says, Compiler Explorer is why you probably heard of me before. I love making emulators for old computers. That's what I've been doing for the last year as I've been on a non-compete. My non-compete ended today, which is why I'm able to be here talking to you. But next week I'll be working at HRT. So we'll be neighbors, I'll be up the street, friendly competition. I also love trying to reverse engineer what the heck is going on inside your CPU, right? Intel famously doesn't give a lot of information about what's going on inside the computer. And that's for obvious reasons to do with intellectual property or whatever, but there's a sort of small but dedicated community of folks who are trying to work out what actually is going on inside. This is my contribution to it, where I was trying to work out how the branch target buffer worked inside some of the older chips. We're going to be talking about some old chips today, unfortunately, because I don't have access to some very, very new stuff because I've been on non-compete for a year and it's very expensive to rent them. But anyway, I've done some research before, and my sort of claim to fame on this is that I was cited in the Meltdown and Spectre paper, which was a kind of nice moment of recognition for this kind of stuff. You've probably seen a CPU pipeline before in textbooks, and I know I've been speaking to some folks who are now sitting very threateningly in the front row, and they have a very deep understanding of everything we're going to cover here. But for the rest of you all, hopefully you'll forgive me doing a quick sort of introduction reminder of what a CPU pipeline looks like. So when I grew up, this is what a CPU pipeline looked like. You fetched an instruction, you decoded it, you executed it, and you wrote it back in sequence. And then you could do this as a sort of production line, as a pipeline, one step at a time. So one instruction was being fetched while the previous one was being decoded, and the one before that's already being executed, and the one after that, before that, is being written back. And therefore, although it takes 4 cycles to get through here, we're still doing one useful piece of work every clock cycle. And that was a big win. Modern CPUs, though, realize that if we can do better than just this sort of single step at a time. We can break the system into sort of 3 broad categories. We've got a front end, where we've got a branch prediction unit. I wanted to talk to you a lot about branch prediction. I actually did a whole bunch of reverse engineering work for it, but I don't have time. So we'll have to talk about it afterwards or in the pub or something like that. But anyway, there's a fetcher decoder, as before. We have a rename step, which is sort of the gateway into a new world. And then after that, this middle section here, this is the back end. Things can happen out of order, which sounds counterintuitive. But in programs, very often we write code which has lots of little parts that aren't totally dependent on each other. You read a value, you add 10 to it, you store it somewhere else. You read another value, you add 20 to it, you store it somewhere else. It's like, well, those 2 things could happen at the same time. And so if you can pick up enough instructions in one go, you can actually do more than one piece of work per clock cycle. And that's what this sort of stack is here in the execute. And that's what the out-of-order system is doing. It's doing some clever dependency tracking, and then everything happens in whenever execution units are available and results inputs are ready. And then finally, we come to the retirement stage, and that's where everything gets put back in the order that the program was written in, so that you don't notice the monkey business that's been going on in the middle bit. Okay. But we're going to be talking specifically about Skylake, which is old, 2019, 2020-ish era is when it was out. But again, my laptop is a Skylake. My desktop machine is a Comet Lake, or Skylake X, actually. Yeah, the laptop's Comet Lake. So these are representative of the kinds of things that actually happen in a modern CPU, but they have changed in the kind of server quality CPUs that you'll be using in your day-to-day job. Where I remember them, I will try and call out the differences, but again, I couldn't test the things that were on more modern machines. So out of order on Skylake is a little bit more complicated than that nice textbook diagram. We have a front end that looks like this. Again, the branch prediction unit we're not going to be talking about. We have sort of 2 parallel lines, the fetch, pre-decode, instruction queue, and then many decoders. Beneath that, we've got a micro-op cache. To the right of that, we've got a queue of micro-operations and the amusingly named LSD. Then we hit the renamer. We're going to talk about all of these things in a second. I just want to just give you a big picture of like where we're going with all of this. What was I going to say about this? There was something I meant to say. It'll come to me. We'll cover it anyway. So anyway, this is the front end. And at this point here, by the time, oh, that's right, micro-ops. I've written micro-op here. So instructions are specifically on Intel are broken into smaller operations, micro operations. So unlike most RISC processors where you're just like adding two numbers together, or you're reading, or you're doing a branch, some of the Intel instructions are crazy, and you can like do some crazy address calculation, which is one number plus another one times 4 plus some offset, and that's the address that you're going to read from. Then you read from that address, then you're going to add to it, and then you're going to store back to it, and that's one instruction. So it makes sense for the poor front end here, which deals in terms of those crazy x86 instructions, to break it down into a sensible RISC architecture in the back end. But we never get to see that. We just have to infer its presence from all the measurements we do on the outside. So that's what a micro-op is. So by the time we get to this point here, we have a stream of micro-operations that are in program order. They get to the renamer, and then they reach the back end, which is a little bit smaller and simpler, and we won't be covering as much of this. If I've got my timings right, we've probably only got 5 minutes of this at the end. But we've got a scheduler, we've got multiple execution units, not the 4 that are here. There are actually many more than that. And then there's a write back stage. Then we have the retirement, and then post-retirement, we have this store buffer commit phase. And again, each of these steps is probably a simplification, but this is mostly built out of measurements that we can make. And by we, I don't mean me, actually, although I have contributed to this in the past. The community of people that reverse engineer all this kind of stuff, I'm relying very much on their results that I'm presenting here. These things are not necessarily found in the Intel manuals. You have to go and dig them out yourself. So I have some references at the end. If you're interested in this and how you can measure it yourself, knock yourself out. It's a really, really interesting rabbit hole to go down. This selection of TLAs, this soup of letters over here, are all the sort of shared data structures that each of the bits of the system can see. We'll talk about those separately, but I wanted to call them out to begin with. We've got a physical, excuse me. We have physical register storage. So while you tend to write programs or see programs in assembly that refer to EAX and ECX and EDX, whatever, the 16 registers that we have access to. 16, what a luxurious number. I know we were talking about earlier that we probably could do with them more, but like it wasn't that long ago. We only had 8 of them, of which 2 of them were used for other purposes. But that is small fry compared to the number of register slots that are actually available on the CPU. And so behind the scenes, it's doing all sorts of allocation and renaming and mapping to take advantage of the extra space it has on the chip. So the physical register file contains all of the actual values of the registers, and there are probably hundreds of those. The RAT is the register alias table, and that's the structure that maps the current EAX to where on earth it is currently on the chip, and other things. There's a reorder buffer which stores essentially a ledger of all of the micro operations that have flowed through the system, and is essentially the sort of reference keeping of like, this is the point at which we know an instruction has been issued, and later on we will retire it in the order that it came through into this reorder buffer. Then there's a reservation station, which is also called the scheduler in some literature. That's where we actually store the things that have yet to be processed, like the actual operations themselves. So like, I need to do an add of this number and that other number, or this number and a number that we'll get when the read that it depends upon has completed. They live in the reservation station. Branch order buffer is a sort of checkpointing system for branch misprediction. Again, I wanted to talk more about this, but sadly, we don't have time. But it's fascinating if you're sitting down and think about what the thing must be doing when it's predicting 20 branches in the future, and then it gets one of them wrong, and he doesn't want to throw all of the work away. And then there's a memory order buffer, which is responsible for making sure that loads and stores to memory still make sense, even though we've reordered everything. So we're going to start with the front end. This is going to be the majority of the talk, and I forgot to start my timer, so I'm going to have to rely on looking at the clock behind you to see where I am. I'm going to use this example, and it's thematic that I have to do it in C++, although we did attempt to write this in OCaml earlier. It did not generate the same code. I will leave that to your imagination. So it's a bit of a made-up thing. It's taking an array of integers, it's squaring them and summing them up. So it's just doing like a rolling sum of all of the integers, sum squares, effectively it is. And it suits my purpose because it compiles to 6 instructions and exactly 16 bytes of machine code. So I'm sure you're reasonably familiar with this, but on the right-hand side, we have this text representation, which is the assembly code, and on the left-hand side is the bytes that the CPU actually reads out. That's the machine code. It used to catch me out all the time. I used to use the two interchangeably, which was foolish. And you don't really need to know, but it's like we read the array pointer, we square it, we add it to our running total, we move the array pointer to the next element, we compare it to the end one, and then we jump back if it isn't at the end yet. Pretty straightforward stuff, 16 bytes worth. What you'll notice, though, immediately, is that each of these is a different length. We've got a 2-byte instruction, a 3-byte one, and there's even a 4-byte one here. In general, x86 instructions can be anything from 1 byte to 15 bytes long. And it's not sensibly written because it's kind of the sort of thing that happens when you take a design from the 1970s and incrementally add things to it while we're maintaining backwards compatibility, which means that sort of everything harks back to these ancient ways, and there's like bytes that say, hey, the next byte is now interpret differently unless it's Tuesday and the moon is rising, and then in which case, so it's really quite complicated to disassemble x86. Anyone who uses ARM or MIPS or RISC-V or whatever, it's lovely. All the instructions are the same length, so it's very simple. But that's kind of why we need to do this complicated decode. Another thing I'm going to quickly show you is an instruction trace of a sort. This comes through a somewhat heavily modified tool called Uica, which is the microcode analyzer that Andreas Abel, who is now at Google, has written and open sourced. And this sort of lets us see an individual instruction's journey through the pipeline. So what we're seeing is one instruction, and then all the stages it goes through from left to right, from time-based. So this instruction takes 16 cycles. On the first cycle here, it's being pre-decoded. It's hitting the instruction queue here. It's being issued, dispatched, executed, and then retired in this particular example. I just want to show an example. We'll have a few more of these up, and I'll explain them a bit more as we hit them. But I don't want it to be surprising when it popped up. All right, first stage, fetching. This is probably the easiest stage, although I'm going to gloss over a whole bunch of really complicated stuff that it does. So we have the predicted instruction pointer. So the fetch unit doesn't wait for the program to definitely go somewhere. It's being told where to go by the branch predictor at all times. And so that's kind of a really interesting aspect that I had never even considered, because you might pick up a bunch of 16 bytes, and until you've decoded it, which is like 4 or 5 steps down, you don't even know if there's a branch in there. And by that time, you've already had 2 more 16-byte chunks of memory that you've pulled up, and you're like, well, I've went the wrong way, right? So, and that's not that would be an unconditional branch, right? If it's conditional, you have to actually even execute to work out whether or not you're going to take it or not. So the branch predictor's got a great job, and it does, by and large, a good job. So the fetch unit picks up 16 bytes at a time at a 16-byte boundary, which means that if you branch to the middle of a 16-byte boundary, then you're immediately wasting a bit of bandwidth there because you're missing out on some of the bytes that you could have picked up in one cycle. The other thing to note here is that I'm not going to talk about caches at all, because that's another 2 hours talk. But this obviously has to liaise with the TLB to go and work out where the heck these instructions actually come from, and the L1, L2, L3 caches to actually fetch the bytes into a 64-byte cache line to then pull 16 bytes of it down. So there's a lot of work hiding here. But the result of this fetch stage is some kind of pipeline of chunks of 16 bytes, presumably with some kind of address that's tagged with them, so we knew where they came from, and it can be checked later on. All right, easy one done. Because the x86 instruction set is so complicated, and because what we want to do is unlock this parallelism where we can run more than one instruction at a time, if the most that we could do in a single instruction, in a single clock cycle was decode one instruction, then we'd be missing a trick down the line. And so what we want to try and do is decode as many instructions as we possibly can out of this block of 16 bytes in one clock cycle. So it's broken down into stages. The first stage here is called a pre-decode stage. And the pre-decoders have a set of kind of flaky heuristics about what these bytes might mean. They're flaky because the only thing that we can think of, again, we being, in this instance, Agna Fogg, is that the only way it can be decoding this, because we have no idea where the instructions lie in here. All we know is they don't overlap with each other. And they depend, of course, on having decoded the previous instruction. And so how could you possibly do it in one cycle? The only thing we think of is that it just speculatively tries to decode an instruction at every possible offset, and then it has a sort of filter step where it says, well, these ones overlap with the one that's come before, so that can't be a valid decode. And again, it's a bit of a heuristic hack. It never gets it wrong, per se, but it sometimes conservatively tags instructions for a later stage of the pipeline that are tagged as being more complicated than they actually are. So we'll get to that in a sec. So these 16 bytes happen to represent exactly that routine that I showed. The predecoder tags it into, effectively just breaks it down and says, well, this is the opcode byte, these are the opcode bytes, whatever. Again, a lot of this now, when I'm pointing at this side here, is my kind of guesstimate about what's going on. It's not canonical. There's no source for exactly what's flowing here, but hopefully you'll forgive me. And the interesting thing here is that what we've done is we've been able to discover where the bytes of the first instruction, which is that mov, the second one, which is the imol, the add edx, the add RDI here. And then for this last one, this is a compare and a jump. And at this stage in the pipeline, it spots an opportunity because although we treat them as two separate instructions, we have to, that's what the ISA is, it's so common. You know, every loop ends in a compare and jump if not equal or something like that. The Intel have decided to say, well, what if we had an instruction which was just a compare and jump as one unit? Well, we could make a new instruction, we could issue it and write all the compiler writers, actually emit this instruction, or we could just spot it in the instruction stream and replace it here. And that's what they do. This is called macro instruction fusion, and it's tagged, at least, in this pre-decode step. So we still don't know really what these bytes are, and again, sometimes the bit masks or whatever it does are wrong. I'm gonna run out of time if I keep doing this. Okay. So the limitations of the predecoder, it can do up to 5 instructions in a cycle, and it does this macro op fusion. Now, at the moment, and by the moment, I mean for Skylake, it may have changed, but I don't think that this one has. A compare and test on anything that isn't memory, which is therefore more complicated, followed by any branch, that's treated as a single operation. An add, subtract, increment, decrement, or an and, followed by a branch on these limited set of instructions is treated again as a single unit, as a compare and branch. It's worth saying that you probably don't do this, although you write compilers, so you might have the latitude to do this. Don't put any length-changing prefixes. These are usually used in like the crazy 32-bit modes to use smaller pointers, but they effectively snarl up the predecoder. It just goes, oops, I don't know, because you can make an arbitrarily complicated instruction out of just putting random-ass prefixes in it. And it just gives its hands up, and it takes, I think it's 3 cycle penalty. If it sees one, it's just like, whoop, I'm out. And yes, the other thing that it does do is it notices whether or not an instruction is simple or complex. And so it steers that instruction to the appropriate decoder. Steering's not really the right word, but I'll tell you what I mean here. So these sort of partially decoded instructions, which again are just blocks of bytes and presumably some kind of sequence. So I keep putting it sort of and seek here. I don't think it uses addresses internally to track, because obviously if you've got a loop, you'll see the same address over and over again. It must be some kind of global sequence number that's used for like, hey, this branch was mispredicted, everything after this is now garbage. So I'm just gonna say and sequence number. So we've got partially decoded instructions, and they're passed on to the decoder. The decoder, there are 4 units, and they're passed them in order. The result of which is, and again, this is me making up my own syntax over here, the micro operations. In this particular example, every instruction is one micro operation. So each one in on that side is one thing on this side here. So one of them is like a 32-bit load through RDI, and multiply and add, whatever. And then this one is a macro fuse one in which I've made up an instruction of compare and jump. Variously, these kinds of things. Okay. There are 2 kinds of fusion. One is the macro fusion we've already talked about. So macro fusion, macro is big. This is how I remember them. That means that 2 big things, the instructions, have been fused into one internal operation. So we've talked about that. Microfusion, on the other hand, is, well, this stupid syntax, or sorry, this stupid ISA that Intel have come up with, it's so common to have an address operand on the right-hand side. While this is logically 2 operations, that is, an add rax, R14 is, go calculate whatever R14 is, go read that from the cache, and then come back and then go to the ALU and add it to rax, right? That's 2 distinct operations. Practically, for most of the time, what if we just made our micro-op like format a little bit wider and had like an optional memory tag, and then we could like put, for most instructions that we've got space, we can say, well, this is both an add and a read. And for the simpler cases, that can happen. And so a micro-fused instruction will later on be actually executed by 2 different parts of the chip as 2 micro operations, but at this point, we can pack it into one micro op in all the queues and things that are coming up down. So we've got microfusion, macrofusion. There is also a microcode sequencer. The microcode sequencer is effectively a ROM with a sort of simple interpreter put on top of it. And so anything that's more complicated than 4 microoperations needs to come from a ROM rather than just being sort of hardwired in the code. And that ROM can either just literally puke out a bunch of microops, here's 15 microops for a complicated instruction, or it can actually have logic in it itself. It can actually go like, oh, okay, well, while ECX is not equal to 0, keep issuing these microops, right? And so for things that are complicated, like locked operations, which I'm sure anyone who's done threading has seen, that takes more operations than 4, or obviously things like rep stores, which is a repeating operation. This is effectively just for the microcode sequencer, just keep emitting the read and write operation until you hit the end of the thing that you're copying. And obviously complicated things like read MSR or Cupid, they effectively runs a little program. It's going to go off and say, hey, what kind of CPU are you? Well, I can return that. And so that's kind of cool. I actually met somebody who worked at Intel, and he said, oh yeah, my neighbor writes microcode. I'm like, what a crazy job that must be to sit there and just like write this stuff that's right at the other end of this. And then the other thing that's sort of done by the microcode sequencer are things like divides. I know they're also complicated, more than 4 microoperations, but it was kind of an opener to me. They're like, oh, that's how divides work. It's got all this acceleration circuitry, but that's how they can short circuits. Like, well, okay, we've reached the point where there's no more bits coming out. We can stop here. Anyway, I've got a thing about divides. You'll learn that in a second. So we've got 4 decoders, but not all decoders are created equal. The first decoder is the real decoder. It can do up to 4 microops. So any instruction that is 4 microops or less can go and be passed by the first decoder. Anything that's tagged as complex, even if it actually turns out to be a simple operation, gets put to the first decoder and the other ones won't touch it. Any instruction that requires a switch to the microcode sequencer has to go through the first decoder as well. So things like that I divide, the first step will be, hey, here's the setup code, and then now we're going to start reading from the microcode sequencer. Decoders 2 through 4 can only do a single microoperation, so only simple things. But this is actually the fused microop, so those adds with memory, that still counts as 1 in this world, even though later on it's going to be broken into 2. We good so far? I'm seeing a lot of nods from the front row, which I appreciate very much. So you can decode 4 instructions or 5 microops, which means that like if you really need to get lots of microoperations out, you can have a 4 microoperation instruction followed by a 1 microoperation instruction, and that can come out in 1 clock cycle. And then the other 2 decoders just have to sit and twiddle their thumbs. 311, 2111, or 1111. Right, and luckily, most things fit into this world, unless you're doing something silly like dividing again. The worst case you can possibly do is just to have a sequence of instructions which are exactly 2 microops each, because they only go to the first one and all the other ones are idle, and then the next clock cycle you generate 2. So that's the worst case. But although I've just banged on about this and it sounds interesting and complicated, and Intel referred to this as the legacy decode pipeline, not that we have any other choices, thanks Intel, we're mostly saved by the next thing we're going to talk about, which is the microop cache and the loop stream detector. I had a sketch at what might be in a microop. I've been sort of trying to, in my mind, construct my own emulator stroke simulator so that I kind of exercise the paths of like where things would need to go, but we don't need to talk about it because we haven't got time. Just to show you some pretty rainbow diagrams, these are some other more complicated instructions that come out as being 2 microops, 3, and 4, although most of these are fused. In the fused domain still, I think this is only 2 and this is only 1. I think this is the only one that's actually 3 microops. But you can kind of see a push racks is like, well, I have to write racks to the stack pointer and then I have to update the stack pointer. Makes sense? Exchange RBX RAX is probably temp equals RBX, RA, the whole switch thing. It doesn't do XORs, I'm pretty sure. Maybe it does. I mean, who knows? And then an add pointer here is one of those really complicated memory operations where we have to read the memory, we have to then add to it, and then we have to write it back. And writing back is always 2 ops because the address generation is separate from the data part of the store for reasons we'll touch later. All right. And then, yeah, because I have to put a divide on here. This is a 32-bit divide on Skylake. They've got a lot better. I mean, I'm sure Granite Rapids is a lot quicker than this, but this, when I first time I sketched this, I got it to print this out, I was like, oh my golly. Yeah, it's like 100 cycles for the 64-bit version. But what the interesting points are here is, like, so we can see that, like, in the first clock cycle, the decoder 0 was able to output these 3 micro-ops. They kind of flow through, and then it switches to the microcode sequencer, and there's a 2-cycle delay here, and now it kind of carries on doing all of its whatever magical stuff is going on here. A note about these are very empirically derived from, like, looking at port pressure, so we're not 100% sure what the individual operations are doing, and sometimes these, when things finish, I'm not totally sure it's right. So yes, we're saved by the micro-op cache. The micro-op cache sort of sits logically to the side of this whole complicated pipeline we've just been talking about. And we're in one of 2 modes. Either we're caching or we're reading from the cache. So unlike like the regular sort of like L1, L2, L3 caches, it's not like every read goes and says, are you there? Okay, no, I better go and do it the hard way. It's just you're in one mode or the other mode. And it's jumps that determine whether or not that process starts. So yes, in caching mode, as we're running through our program, the micro-ops that the translation engine has been doing, sorry, MITE is the micro instruction translation engine. That's, again, Intel loves coming up with complicated names for things. It's or the legacy pipeline. They get pushed into this cache, and then they're just sort of written into the cache. Or if a jump happens and the part of the branch prediction or whatever part that notices that the destination of that jump happens to be in the micro-op cache, then we start streaming instead from the micro-op cache. And this is the happy place. You want to be in this situation. So the result of that is just also micro-operations. The micro-operation cache is the weirdest cache you've ever seen because it has a really difficult job. If you think about a normal cache, like an L1, L2, whatever, you've got a one-to-one mapping. It's like this byte is in that cache line, and then you just fetch the whole cache line around it, and you whack it in the cache, and you're done. But if we jump to an address that's not on like a cache line boundary, then, well, we decode that instruction, but we can't reverse back and say, well, what was the instruction before it then? You just have to kind of start at that point. And so there's a lot of really weird restrictions on it. This has changed a lot since Skylake, but the Skylake has 32 sets by 8 ways, and each way, each cache line, has up to 6 micro-operations in it. Some of the micro-ops take 2 slots, so like if you've got one of the MOV with a 64-bit value, you need to have 2 slots in order to sort of store the 64-bit value. It is inclusive with the L1I, which is a clue into how it's implemented. And then the weird thing here is that there are no more than 3 ways can be used by any 32-byte of code. And this, to me, smells like they had hit a real snag because morally, this is very similar to the trace cache that the Pentium Pro used. And I don't know, you all look too young. But the problem with that was that you have as many entries in the cache as there are traces through your code. And so very quickly you blow up as the traces change. So I think they try and limit that by saying if any block of memory, small area of the program, needs more than 3 lines, then we're probably in this case where it's about to start monopolizing the whole cache. We'd rather throw it away and prevent it from being cached at all. It's worth saying that, yeah, any branch, even a not taken branch, ends a cache line, and then it starts caching from the next thing. So it kind of tries to find the sensible boundaries. But one of the sort of like take-homes from this is if you're generating code, if you have more than one entry point into the same 32-byte block, then you might be not using the DSB as effectively as you like. And I know that it's quite typical in compilers to like start with a, hey, let's do some setup code. Then we jump to the end of the loop that then does like the loop end, and then it jumps to just below the setup code to like then run round. And you're like, now I've got 2 entries. But so you have to think about it. 2 is probably fine. Yeah, I forgot to say this before, but like, this is why we align loops on 16-byte boundaries typically, so that you get the benefit of the fetch system picking up the loop. Okay, but yes, in newer machines, it is more like you can have 6 ways in 64 bytes. So it's a bit of a weirder thing, more closely tied to the L1 cache. All right, I think, yes. And then it can deliver anywhere between 4 and 6 micro-ops per cycle, which means that even if they're complicated or simple or whatever instructions, you can get a pretty consistent stream out of it. The literature says 6. I could only ever measure 4. So I don't know if, whatever. All right, yes. Yes, the loop stream detector. The loop stream detector. So in between this sort of source of micro-operations that's coming from either the legacy system or the cache, there is a queue. Obviously, we love queues. Queues buffer if the renamer or the execution unit is sort of backing up a little bit. We've got a bit of space in here. But this queue effectively is a big circular buffer of a couple of hundred entries that we're writing on microcodes in program order in. And what the loop stream detector does underneath is it says, wait a second, you've jumped to a location that's actually already in this buffer. It may have already popped off the end of it, but we haven't overwritten it yet. Wait a sec. Wouldn't it be better if we just kind of held that part and just kept streaming back that same sequence of events over and over and over again? And so that's what the loop stream detector does. And that means it can turn down the whole front end. There's no caching that has to be done. There's no decoding. It's just brilliant. But it's relatively small. And it has limitations. So it spots loops that fit in the queue entirely. It can deliver each cycle up to 4 microoperations, but it can't deliver more than 1 loop iteration. So if you have a really small loop or a loop that doesn't fit into a multiple of 4, then you might get if it was 5, you get 4 in the first cycle and 1 in the next one, and then 4 and then 1 and 4 and 1. Except it can unroll. It actually spots the longest thing it can get, up to 8 times in the Skylake, so that it'll actually unroll that loop effectively in hardware and go, well, now if I take my 5 iterations and I do them 4 times, my maths is not good. 5 4s are 20, 20 divided into 4. Yes, I think we're good, right? Yeah, something like that. So then it would just fit, and then in every cycle it can stamp out 4, which is pretty cool, which is great. But why was it in parentheses and why did it have a star? Well, it's disabled on Skylake. Which was reported by due to a massive thing, and this is where I'm actually going to have to bring up my notes. Sorry, you're going to have to see speaker view for a second because, yes, here we go. It was described as a nightmare-level bug in the Debian fix. Short loops using the AH, BH, CH, the high part of the 16-bit register and the corresponding wide register may result in unpredictable system behavior. I mean, whoa, that is scary stuff. So props to them. I don't know what it was, and there are people in this audience who probably can tell, but something about the OCaml runtime or the OCaml compiler liked to do this. Like in a loop, it would use the high 8 bits and the low 8 bits, maybe tagging. I don't know, I'm looking over at you two because you're my favorite two to look at. But yeah, it was found by some folks in the OCaml community and reported, and then Intel determined it couldn't be fixed, and they just issued a microcode patch which turned the whole thing off. Wow. Okay. Yes, OCaml. We did weird things so you didn't have to, right? Okay. Renaming. So now we get to the cool part here. Now, again, those of you who have done college level courses in this kind of out of order execution, this is probably meat and drink, but I'm going to go over it anyway because it's just really interesting, and the penny dropped for me writing these slides about how important this whole process is. So the renamer has probably the biggest job in the entirety of the front end because it has about 3 different jobs. The first thing that happens is that now the micro-ops have reached this point. This is like the first point where we can say this is definitely going to happen, so we're going to put it into, it's definitely speculatively going to happen. It might be undone later on when we discover we shouldn't have done this way, but we're going to write it into the reorder buffer, which just says this instruction happened or will happen. We also then rename to physical registers, so we take the EXs and the RDIs and whatever, and we use this vast array of on-chip resources to actually use for registers, and again, I'll talk about that in a sec. And then it also takes the micro-operations that were represented and shifts them off to the right execution units to sit to wait. So they'll sit in those scheduled until either the execution unit is ready to accept a new operation. Maybe there's a multiplier that's backed up, waiting, and there are other queues, other instructions ahead of it. Or maybe this instruction depends on the result of a previous instruction that hasn't completed yet, and so it'll sit there and wait until all of its dependencies come in. But this is the point at which we kind of fan out into all the various data structures, and then the out-of-order system picks it up on the other side. Amazingly, although it's doing all this complicated work, it can do 4 micro-ops a cycle. This is staggering. Maybe this is the kind of thing that in hardware is a lot easier than it sounds, right? This is the kind of thing you discover. So the first thing we do is the reorder buffer write. This is just to have our ledger for in-order completion later on. There is a process called unlamination that happens at this point. So at this point, sometimes the micro-op that came through, even though it wasn't micro-op fused, is determined to be, this is actually more complicated than I can do in a single unit. And so it'll break it up at that point into multiple pieces. Some of the more complicated addressing modes sometimes fall into this category for operations that could otherwise go to the adder. It's well, the adder can't do this. I'm a little vague on that, I'll be honest with you. But unlamination is a thing that can generate extra micro-ops at this point. There are 224 entries in the reorder buffer. That is the sort of top end of how many things that can be possibly in flight at once that are in the system being executed. That's more like 500 on, I'm looking at you two in the front again for this. I think it's about 500 in Granite Rapids and above. So that's a place that they have changed a lot and expanded. It kind of looks something like this. We have some kind of sequence number for each of the instructions in sequence. We know the information it needs to track is where are we writing to, and then what rename happened. We'll get to why we need that information. It's sort of weird that we need both the source and the old version, partly for undo, if we were to talk about branch stuff, but partly for another thing that I'd never considered before. And then we've got some kind of type of information. There's some to do with like if it's a branch, where its sort of restore state might be stored. And then the important thing over here is that while this is all written to in this rob write, this part over here, the execution and exception, is going to be written to once the instruction is actually finished. So it's going to go through the rest of the pipeline and come back here. And so in my sort of example I've got up here, this first instruction, this load, has completed, which means it's gone through the system, it's finished, it's done with, and it could be retired at any point. The retirement unit could finish it off. And you can see, I can't remember what I did. Oh yeah, and it's got a source down here of P22. Yeah, there's sort of an implied dependency there. It's not really that important. And again, we don't really know what this looks like. This is the minimum set of information I think it needs. The issuing step is where we actually take the live to be calculated micro-op and give it off to these execution units. The execution units are in two big blocks that have many ports on them. It's a weird terminology. But there's an ALU unit that has all of the things to do with arithmetic and logic, as you might imagine. And then there's a sort of memory system, which only does loads and address generation. And they have different numbers of entries. They are presumably balanced by some kind of internal pressure inside both the layout and the complexity of those things, and also the experiments that Intel do in terms of how many of each type of instruction they typically have live at once. The issuing determines also which port within each of these, so these are further subdivided, but at this point, this is when it's decided where it's going to ultimately go. So even if it's an add, and there are like 3 different locations on the chip where that add could happen, we decide now at rename time which of the adders it's going to go to, which is a little bit myopic because by the time it actually gets ready to run, maybe that's not the best choice of adder now. Maybe there's some free adders somewhere else, but it's useful to know. And obviously, it's a simplifying assumption here. The algorithm has been reverse engineered with high probability that they got it right. And it's kind of as simple as you might imagine. It's to do with like the balance of how many operations have gone recently. And it tends to pick the higher port numbers if they're more free, if there's a tie. And then it's sort of, of the 4 instructions issued, the 1 and 3 go to the top place, best place to schedule them, and 2 and 4 go to the second place. So it kind of tries to balance them as well. Again, it's documented. You can go read the Python code that does the same thing. And at this point, also now, separate from unlamination, which actually makes 2 entries in the reorder buffer for an instruction that we notice later on is a bit more complicated, anything that's actually micro-fused, that is like the add with the RDI, gets separated into the load component that's going to go over here into the load unit, and the add part that's going to depend on the load that's going to go into the ALU component. So the difference between unlaminated micro-ops and micro-fusion is that this only has one sort of slot in the output buffer, in the reorder buffer, whereas the unlaminated stuff actually takes up more resources in there. Not that that's a huge problem with 224 of them. All right, good. So again, I think really the reason for me putting this up here is to sort of show you what information is being stored in each part, because for the longest time I had reservation station, which is the scheduler, sorry, and the thing that the issue is writing to, and reorder buffer kind of mixed up in my mind. So this is more my symptom of me explaining to myself so that I could talk to you about it, but hopefully you'll forgive me. So it looks something like this. We have a bunch of operations, micro operations. These are no longer in any particular order. And we have maybe 3 sources that can happen, and we've got a destination that it's going to write to, and it's an add. And this is a guess. Now, I have been unable to find anything that tells me whether or not the values of known quantities are stored in the scheduler in this sort of micro operation, or it's just a reference. Now, the way that I've chosen to show this is that this one has 2 resolved sources. So these have already completed the instructions that generated these 2 numbers. Maybe this was actually in the opcode and this one was like reading from a register. These 2 have already completed, so I've written the values in here. And then for these guys here, I've shown that like I'm waiting for the previous instruction that's, well, this guy, in fact, who's going to write to P24. I'm going to wait for him, and then when he's completed, he'll tell me what the results are, and I'll put it in here. We don't know if that actually happens, as in this broadcast action causes the things to get written, these slots to get written to. There's some circumstantial evidence that maybe it is, because there's a broadcast bus, but it also opens more questions about what happens if you are issuing instructions that have 2 known quantities, and then we have to read an arbitrary number of like physical registers in 1 clock cycle. Like if every instruction had 3 sources, each of which wasn't already in flight, then you could imagine that issuing 4 of them means that we have to read from the register port 4 times, 3 times, and that doesn't seem realistic either. So, and no one has been able to find a limit to how many you can read, unlike Sandy Bridge, which had a very, very limited number of read ports. So something magic is happening, we don't know what. Anywho, let's talk about renaming. So let's talk about, first of all, the nuts and bolts of renaming. So what renaming is going to do is going to unlock more out of order opportunities down in the rest of the pipeline. And what we're going to do is we're going to break any dependency that we can, because many times when we say EAX, we just mean the current value of EAX, and we're going to do something to it, and then we're going to throw it away, and then we're going to load something new into EAX, and we're going to just keep doing this process over and over again. And those things are separable from each other. And so one example of something where the values of the registers don't depend on an earlier value of the register is a loop, because we're going to read into EAX every time around the loop, and we're going to do some work with it, and then we're going to store it into a value or whatever, and then we're going to start the loop again at the bottom here. So if we can break that dependency, it means that we can run maybe 2 iterations of the loop at the same time, or even more. I'll show you what I mean. We've got pictures coming for those of you who are furrowing your brow. So the way that this works is we have a table that tells us where each register currently is. So which of the physical registers, and again, this is my made-up syntax, P whatever, currently contain the most contemporary value of racks. So racks is P39 and whatever. And then there is a free list of registers. These are registers that are currently spare chip real estate going spare. Fabulous. For every time we read from a register, we're going to use its current value in the RAT. Every time we write to a register and completely replace it, it might as well be a new register. So we're going to pick a new one off the free list, use that instead, and then update the table to say this is where the racks register is now. So this first instruction, we're reading the RDI register, and we're going to go and fetch memory from it, and then we're writing to EAX. So it really doesn't matter what was in EAX before. So P39, don't care about you. So what we're going to do, we're going to rename this to be P45, and hopefully you saw that kind of went that way. It's me popping off the front of the free list. This is in hardware, remember, by the way. This is like pretty impressive. And then P22. And then this mul here is EAX with itself, right? I'm squaring EAX and I put the result in EAX. And I know the opcode doesn't have 3 operands, or it can do for some multipliers, but it's been rewritten into this nice risky form by this point. So when we read the EAXs, we're going to use P45, and then when we write, we're going to use a new one, which will be P46, and this is indeed what happens, and so on and so forth. We can go through the rest of it here. And now we've got this whole rewritten set of micro-operations that are phrased purely in terms of physical registers only. And we've sort of encoded the dependency between instruction values by, if you follow the P45 in here, it's used here, and then it's done with. So that's helped us. So this is what that loop looks like, or rather loop iteration and a half. So I've got 1.5 because it fits on the slide. If we didn't have a rename, this is what it would look like. So the first iteration of the loop is from here to about here. And you can see that the next iteration of the loop can't even start because, well, I can't read through RDI until I finished adding to RDI from the previous iteration, right? Because it's like, I have to wait for it, right? And it couldn't start, we couldn't add 4 to it to move it forward until we'd finished reading the memory address at RDI, because presumably I still need the RDI register or whatever. Again, I had to hack the code so badly to make it do this, and I then went through it and sort of manually fixed it up. But you get the idea. If we were to sort of show you the zoomed out view, it looks like this. And if you see these kind of diagrams, you can squint and you just look at the R's, really. And you kind of look down there. And this is, mostly throughput rather than latency, but it's 10 cycles an iteration. Doesn't seem totally unreasonable. Obviously, you'd use SIMD if you were actually trying to do this for real, right? And you get more per iteration, but 10 cycles an iteration. If we rename it, on the other hand, it looks like this. So on the first cycle, we've already queued 5 of our instructions, and we've issued 4 of them. The first and the fourth one can already complete on cycle 6 because this add can be running concurrently with the load as they don't depend on each other anymore, and so on and so forth. And you can see every time there's an E, there's usually a D underneath it because the E means it's finished executing and the results become ready and immediately can be used in the instruction that depends upon it. And this is evidence for the broadcasting theory of this, where it kind of completes, it just goes, anyone who cares, P45 is now 27. And like, oh, cool, I got it. And then he doesn't have to wait another cycle. Okay, I think we've got everything. So that looks pretty cool. But if we zoom out, it's like 1.5 cycles in iteration. It really makes a difference. It's super cool. All right, I've labored that enough. Right, let's talk about my favorite instruction. XOR, EAX, EAX. You've all seen it, right? Yeah. Why the hell does it do that? Anyone want to shout out? No. Nobody wants to shout out. Sorry, did some? It sets it to 0, but why not just do mov EAX, 0? Come on. Smaller instruction, it is. It's a smaller instruction. But mate, there's more. XOR AX, so let's go through it first of all. So exclusive ORing a number with itself always leads to 0, right? And because of the stupid syntax of x86, this is EAX XOR equals EAX, right? So it ends up with 0, fine. The compiler loves to do it. But the cool thing is the CPU knows that you love to do this as well. And so it goes, oh, if you're setting a value to 0, I don't need to do anything at all. All I'm going to do is I'm going to arrange to have a physical register that's always the value 0, and I will just rename it. Okay, RAX is now P00, and any kind of thing that reads from it later on is just going to get the value 0, right? We're done here. Doesn't issue at all. So although it's written to the reorder buffer, it doesn't go to any execution unit. It doesn't take up any resources at all. It's magic. We can also do some oneing idioms. There are some parallel oneing type things that can generate an all one, so presumably there's some other magical register that happens here. Okay. We can also do move elimination, because if you think about it, if I move RBX into RAX, all I've done now is I've just got 2 names for the same register. So we just have to update the RAT and say, well, you know, RAX is now P88, which is incidentally where RBX is at the moment. There's no issue. This is no issue. This doesn't mean there's no problem, because there's a problem. There's no issue. There's nothing written. There's no actual work to do. There's no actual ALU unit that needs to be done. But there is an issue, because this actually does introduce a complication. It's surprising. There are limits. Have I got a slide? Oh, no, it's here. I've gone ahead by one. So there are limits, right? Because now we're allowing a single physical register to be aliased by more than one architectural register, which means that suddenly we either have to do reference counting to determine when we can free that thing back up again, or we need another trick to determine when everyone's finished with that particular physical register. What it seems to use is it has 4 slots for aliases, and once one of those slots has been used by having 2 registers point at the same thing, until all of those registers have been overwritten, that P88 is now locked. It can't be freed. And also that slot can't be used by anything more. So you can do 4 mobs in a row and they're all free, and then after that it becomes really expensive to move between registers until you overwrite both the source and the destination that both aliased. That has gotten better, and I think they now use a bitmaster track things in a much more clever way, because on older Lake and onwards they have another trick. And I know that I said I was with Skylake, but this is just too cool not to talk about. Because, you know, adds and subtracts are so straightforward. What if the renamer goes, well, hang on, an add with 1? Why don't I just rename it as Rax's P88 and just remember it's got a 1 added to it? How cool. So again, small increments and adds don't take up any resources at all. They just get written as sort of a housekeeping issue inside the RAT. We have to pay the price at some point. 2 reasons. One, the range is only between minus 1024, so it's got like 11 bits of range. And then if it hits that limit, it actually does issue the micro operation that says, oh, fine, add the thing, and then we know where we are, right? And then, of course, after that, it can be renaming from the new value, so it's pretty cool. There's also, interestingly, if you think about what this really means, is that when P88 becomes ready, if it were depending on it, anything that depends on P88 has been given the burden of having to now actually do this damn add, right? And so many of the instructions, that's fine, right? It's like, okay, I'm reading from P88 and there's an adder that kind of runs in parallel, and then by the time the result gets to me, it's already had that offset that needed to be applied to it. But the shift, like logical shift, for whatever reason, it takes a cycle to do it. Every time, if you, and this is how we discovered this was going on, because this is not in the literature anywhere, right? If you do if you like do mov racks, 10 and a shift, you'll measure the shift takes 1 cycle. If you do mov racks, 0 inc racks, and then you do the shift now takes 2 cycles because it pays for doing the add in a single cycle beforehand. And we don't know why it does that, but the guess that we have is that for things like variable shifts, where you're shifting by the value of another register, because the barrel shifter needs a lot of setup time and it's a lot of circuitry to do that kind of 64-bit shifter arbitrarily, we figured that it probably needs the results a lot earlier in the cycle, and so it hasn't got time to do the add and then set up this thing. And then rather than them just blanket the shifts that have variable shifts, they just said all shifts. Or it's a mistake. I mean, mistakes have been made before, as we've seen. So this is super cool. It's really interesting. There's a whole blog post, which I think I've got at the end, that's fascinating digging into this. OK, we are 50-odd minutes in to the presentation. I don't think I've lost too many people. Most people's eyes are still awake, open, or they're awake, or both. And this is the summary. This is where we are. But this is the meat of the talk, just getting to this stage. So we've got a predicted program order, which gives us a sequence of instructions, those instruction pointers, which are then fetched. They're decoded into microoperations. Those microoperations are renamed, and then the reorder buffer is written to in program order, and then these sort of microoperations that are pending execution get written into the scheduler. Great. OK. The back end looks really simple in comparison, but it does hide, kind of the thing we care about, actually doing the work, right? Everything is just a preamble. So I've already said reservation station. The scheduler and the reservation station are 2 names that Intel use interchangeably, or certainly Agnafrog does, and so that's where I'm getting a lot of my information from there. The execution and then the write back. So it sort of looks something like this. We've gone from this nice pipeline to a big soup of things that can be done at some point. And so we've got the 2 schedulers, whatever we call them, reservation stations, that have their 39 entries that are just sat there waiting for either all of their operands to be ready, waiting for their operands to be ready and for an execution unit that they've been tagged to go to become free. So that's what they're sitting there in these queues. But again, the queues are not really in any order. It's just whatever's ready. We've got the reorder buffer. The write back for the reorder buffer is just to say this instruction is now done, we've completed. There doesn't have to be any other values. Now, way back when, it's sort of like the, oh crap, what was the one before Sandy Bridge? I'm forgetting now. They have such stupid names. I really wish they would come up with a good naming system. Anyway, earlier on, the reorder buffer actually contained the physical registers. Effectively, it just used the reorder buffer as the physical register store, and so the results of everything were written back into the ROB, but that's no longer the case. They live down here because we added, vector operations, and if we had, 512-bit wide slots up there, it's a lot of waste for a lot of, unless you're writing AVX 512 all the time, which maybe you are. I know you can't tell me. Maybe you can. No, so we've got reservation station here. Yes, we've got various ports attached to these reservation stations. And sort of broadly, the big picture thing is every clock cycle, the scheduler says which of these microoperations is ready to run, and it issues them to one of these ports that has many actual logical units. You'd think that this was just like an adder, this is a multiplier or whatever, but they each have different usages. And then those are pipelined themselves, so they have their own pipeline, but they're fixed length, and they come out. And when the result comes out 5 cycles later, 3 cycles later, whatever, it comes back into this write back bus, and it sort of says, yes, P47 is now 127. Maybe it's written to the physical register file. Well, it's definitely written to the physical register file. Maybe it's written to and snooped on by some of the other entries that are waiting for that result, and they become ready to run. And then the whole process just keeps going until there's, well, it just keeps going. There's no, never stops, right? Fabulous. Okay, so looking at the ports that we have, this again is Skylake. We've got a whole bunch more on the more up-to-date Granite Rapids-y type things. But by and large, you can sort of see where all of the engineering effort went down on this poor thing that gets all this work here. So there are 3 units that can do integer and vector operations on like simple integers. There's 2 that can do the shift, 1 that does the permute, some string operations and whatever. The number here is the latency, incidentally. If you're doing it wrong if you're using x86 for what it's worth. And so the execution ports over here are doing all arithmetic type stuff, except for the kind of like, here's one of these kids that doesn't look the same as the others, which is the store unit, which is weird that the store unit doesn't live in the load store unit, but whatever. Over on this world, we've got a bunch of load ports that can do work, and they can also generate the address of the store, and then one sort of really kid that can only do simple addresses, and therefore, I don't know what happened here. Maybe they were like, they copy-pasted it twice, and then they didn't have enough room for it, so they edited it a bit. And well, we can't do the complicated addressing here. We'll just have to have that kid do that. Cool, right. I forgot where I was going with this. Never mind. I think you get the idea. There's a lot of things that go to different ports. Yes. And so, yeah, typically it picks the highest port of the available ports if there's a tie, because the higher ports can do fewer things. And so if it can do a vector shift in this one, it's kind of freeing up ports 0 and 1 to do more of the other weird thing that might be coming down the line. All right. So the address generation stroke load unit generates addresses. Surprise. And it does the loads. Hey, who thought? What does that really mean? Well, we're going to have to introduce something called the MOB, the memory order buffer. This is probably the most complicated part, and we only have like 4 minutes to do this, so there's going to be necessarily some simplifications here. Some of the simplifications is in my understanding. Some of the simplification is that no one has come up with a way of measuring exactly how this works yet, and some of it is, I don't know, user error on my part, I don't know. So there are 3 kind of parts to this. There's a load buffer and a store buffer. And there are some predictors, which are absolutely bonkers, and we talked about earlier, and I don't think I have time to go in the depth that we went into at the table, but there's predictions all over the place. So the store buffer holds all of the stores that have not yet gone out to the real memory. And now remember, everything we're doing is speculative at this point. Until the instruction retires, we haven't got cast iron guarantee that something upstream of it that happened in program order before it hasn't gone, oh, I just divided by 0, or oh, I mispredicted a branch, or anything like that. So until it gets to that retirement unit, we can't let the store go out to real memory, right? So we have to hold it in this sort of holding pattern. But of course, if I store to memory, and then the next instruction reads from memory, I might reasonably expect to see the number I just stored in memory, right? That would seem quite bad if it didn't. So I have to do something about this. So this store buffer has many, many hats. One of them is to hold the stores until they go out to memory. The other one is to kind of handle the loads that have come after it that might need to read from the things that haven't yet committed. So it's broadly broken into these 2 parts where we have the address calculation and the data calculation separately from each other. And this is why this data unit lives in the ALU, because where does the values that are going to be stored come from? Probably the ALU. And the address is generated by the address gen. What we're doing here is that by separating them, most of the time, maybe not all the time, or some of the time, let's just go with some of the time. Some of the time, you know what address you're going to be storing to earlier than the data that's going to be stored to it. Like, you square root something 20 times in a row, so you've got this huge long dependency chain of square roots, and then you store it to address 20, right? I know that it's going to store to address 20 pretty early on. I'm going to have to wait 500 cycles before those square roots have all completed. Why do I care about the address? Well, if I've got a load coming on and it's not to address 20, I can do that load. So I need the address more than I care about the data for the purposes of letting other instructions that are later in the flow get their results. So we have the address, we have the data, we have how wide that is, whether it's completed or not, and whether or not it caused a fault. Obviously, again, if we cause a fault, but it was on a path that is not got to because we're going to divide by 0 before we get to the fault, or Spectre and meltdown notwithstanding, then we don't want that to actually take effect. And so when it comes to retirement, we'll check whether it was a fault or not. So stores, we have to wait for those 2, address calculation and the data operations, and then we sit in that buffer serving the incoming reads, and then eventually we actually commit, and that happens way much later after we retire this, once it's retired. The load buffer, on the other hand, stores the loads that are happening and some status about the prediction stuff that I alluded to, but I'm not going to go into. But this is used for tracking some guesses. It makes some intelligent guesses about whether or not a load may never alias, in which case it can issue it really, really early. The problem with that is if it gets it wrong, it's incredibly expensive. It has to do a whole bunch of state clearing to kind of undo the fact that it let a load happen that was actually dependent on a store before it, but it didn't run. There's not like an undo mechanism for that. So it just throws everything away. So we have, some kind of reference to where the ROB is, how wide it is, and what address it's going to, that it's been served from. And again, this is also the order in here, and there's the store color here is a reference. It's called this in the literature. There's a pattern that talks about store color. They don't go into any details of what that really means. If you look at the RISC-V implementation of this, it uses a complicated bit mask, but effectively this is some way of it saying which stores could potentially have affected this load, as in where is it in the sequence of stores, so that I've got some way of tying the things together and knowing that like once all previous stores have been accounted for, I can do this load. All right. So loading is really, really, really complicated, which is one of the other reasons why it's slow. Not just, we talk about L1 cache, it's like, hey, it's 3 or 4 cycles to get to L1 cache. It's like, it's got to do all this as well, right? First of all, we do some prediction about the ambiguity. Again, out of scope, unfortunately. We have to wait for the address to be calculated. Hopefully that's quick. And then we have to check the store buffer. Now, if we get a hit in the store buffer and there are no intervening stores between the hit that we made and anything that hasn't yet been resolved, then we know that no store earlier than this load can possibly affect the value other than the one we found. And we can go, hooray! We don't even have to go to L1. This is like L0 cache. Here you go. Here's your number. If that's not true, if we miss, as in we don't find anything in there, but there are also no stores that haven't been resolved earlier than us, we're like, hey, there are no stores that are in the queue that have not yet been flushed out to memory, so we can just issue the load now. And then it will actually finally go to the L1 and start the whole process of reading from memory. And obviously the load finishes and eventually completes and comes back, and then we kind of send it off to the program. It's a miracle that any of this stuff works, right? And if not, if we're still in this sort of ambiguous state where there are unresolved stores, we just have to wait. We have to keep going and sit in this queue until all of those stores have been resolved, which is why we try and predict if it's going to happen, and sometimes that's worth it. Okay, yeah, there's some pattern number here, which I'm sure you're not allowed to click on because of all the legal things, but let's not go there. All right, the other thing that the memory order buffer is involved in is all of those horrible locked instructions that you want to do. Fences, so like store fences and load fences are like operations that will cause those things to drain out before any further instructions that can issue loads can happen and that kind of stuff. And it's sort of vaguely alluded, I'm going to put just the words total sort of here, but my confidence in this has been irredeemably shaken by our conversations earlier. Where's Andrew? He was here earlier, I'm sure. Yeah, there is. So there's definitely some things that go on with this, but that happens sort of later on. So finally, we get to talk about execution. We are now exactly at an hour since I started talking to you all, and we're going to talk about execution, which is luckily the most boring stage because it does what the old CPUs used to do, right? It's pipelined. There are machine traps. Interesting, this is where floating point assists happen. If whoever has ever hit the hideous performance cliff of denormals, there are some nods in here. To the best of my understanding, what happens here is that so the floating point unit can't handle numbers that are like not 1 point times 10 to the minus whatever, or 2 to the minus whatever. So for very, very, very small numbers that are below float min, whatever the thing is, there has to be special casing for it. So the hardware can't do it, but it can't determine that ahead of time. So by the time it gets to this point, the multiplier of the adder and the divider goes, oh, crap. Shit, right, what do we do? We've got like a number I can't deal with. It just has to essentially flush the pipeline, and then it goes back to the microcode sequencer and says, can you just generate me the code that can handle this, please? And you're like, what? Dynamically, like, undoing, as a de-optimization kind of thing, like a JIT de-opt. Yeah, it's crazy. Anyway, and the execution ports, we hope that they're balanced. Like in terms of the latencies, if I go back to the slide before, it used to be the case you could sort of see, all right, I won't do it now. But like they try to like make it so that there aren't different latency numbers of instructions, because one of the other things that happens is if 2 instructions on an execution port completed the same cycle, like you've got a 3-cycle guy and a 5-cycle instruction that was issued 2 cycles earlier, they both want to complete in that last cycle, and that would delay one of them. So they try to avoid that by like coming up with sensible, everything's a multiple of 2 over here, and then we do this type of thing, or whatever. There's some tricks to it. Gosh, where are we? So that's what I mean by that. And then, yeah, we've talked about this. The write back stage is the results are broadcast. They're written to the permanent register file, physical register file, not the permanent register file, that's different. And it's marked complete in the reorder buffer. All right, retirement. Retirement is the easy bit. All we're doing, all the retirement system is, yeah, we're all trying to retire. I know. Earlier perhaps than not, but finally everything is done. So that reorder buffer is essentially that ledger again of all instructions that flow through the system. The retirement system is trying to pick up as many completed instructions as it possibly can and say, okay, these are now done, and they can be freed back off. And that's the other thing, it does do the freeing. So this is where the registers that were renamed are now freed back to the system as they've been all the way through the system. But of course, the opcode that we've just seen, it's not that the register that we just got written to that we're freeing, it's whatever it used to be when it was renamed right back at the beginning of the pipeline. So we know that when we complete the register that replaces EAX completely, and it used to be P88 and it's now P50, at the point that it retires, P88 is now free. So that's when it gets chained back onto the list. And that's also why that is simple, provided you have no aliasing and no one else has also got P88 at that point. So this is where exceptions actually get handled. We talked about this as just a flag, and then that's when the whole thing goes horribly wrong. Hopefully you're not doing too many exceptions in your code. And not exceptions like C++ exceptions, I mean exceptions like machine checks and divide by zero and memory stuff. The stores are also marked as senior in that memory order buffer because they're going to continue to live in there until they actually get flushed out to the real memory. And the retire system can do 4 microops a cycle, which is very rarely a limitation, but if you can sort of prove it with very, very pathological code. Yes, and then later, the last stage is, it's not really a stage at this point, it's just that the store buffer is kind of retiring stores in order as well. As they become senior, that means they can go out. That means the instruction that caused them to become ready has completed, so they're okay to be committed. And then some magic happens, something total store order, some kind of liaison with the chips on the die and all the other subsystems. And this is where I can tell, as far as I can tell, this is with the RFO, the read for ownership, that actually is the kind of when we talk about cache ping-ponging and false sharing. This seems to be when it happens. I was very vague on this, honestly. I was trying to work out where it could possibly happen. I should probably talk to you all and see if you have opinions on that afterwards, but it seemed it. Okay, right. Well, that's it. It's pretty straightforward, right? And to think that I was going to talk to you about branch predictors as well. But, where's the next thing? There it is. Yes, a conclusion. There's not really a conclusion to this. The whole talk is the conclusion. It's like this thing is an amazing edifice that's been built, right? It's amazingly complicated. The kind of advice, and I feel like I'm teaching your grandmother to suck eggs here, is like, you all know this, do things simply and straightforwardly. Don't do divides. Again, integer divides, that is. Floating point divides, fine. I don't care about those. Small aligned loops are good. Let the renamer do its work. Again, I wrote this before I had the conversation with some of your experts, and the call for more registers was really interesting to me because I hadn't really thought about the implications. But my small loops seem to work okay, so I'll stick with those. But yeah, so the renamer is very clever at doing its work. You shouldn't need to worry about having more registers. With now a massive footnote, speak to these people. Yeah, I'm sure you all have questions. I've got a whole bunch of references here that you can go and look at. I will make sure that these slides are available to you all so you can go and look through them all. Thank you very much indeed. All right, I got the cube. Is there anyone brave enough? I have swag as well. You can come and get stickers. Before you go, you can come and grab a sticker, or I have one special, or two coasters, which are not very exciting because they're made of cardboard, but I'm trying to bribe you to talk to me. Somebody speak, go on. Oh, there is a question, hello. All right, I'm gonna try not to hit anyone, but I'm sorry. I don't think I signed anything to say I wasn't causing physical damage.
Are the physical registers like equally as wide?
Good question. No. So the physical register file is broken into different pieces. I thought I had the numbers up on one of the slides. Maybe I did, but I didn't talk about it. There are a different number of registers for different types of, different number of physical registers for different types. There are like several hundred flags registers because they're small and pretty much every instruction affects the flags, but almost every other instruction doesn't give a shit about what those flags were. So you want to try and rename them away and make sure there's no false dependencies. For the AVX things, registers, there seems to be a batch of like full width 512-bit physical registers, and the renamer seems to want to use those only when it knows that it needs them. Otherwise, it tries to use 256-bit. Again, it's trying to save some kind of real estate. Again, I'm waving my hands a bit here because I haven't had full experience personally of this, but from reading in the literature, there is some kind of cleverness about the allocation of those. And obviously, then the 64-bit general purpose registers there's just some couple of hundred of them, and I'm going to.
But they're at least 64 bits wide.
They are at least 64, yes, and they're made for each type of register, so they're at least 64 bit wide. Yeah, another thing to note, I was very cavalier about saying racks and then showing things that had EAX on them and all that kind of stuff. Now, we all know that they are the, quote, same register. It used to be the case, again, Sandy Bridge era, that if you wrote to, say, AX, then the register allocator gave you a new AX, racks, like EX effectively at that point, and then it also wrote out an opcode that was like and or it with the remaining part of the old version of that register, right? To kind of combine them. That seems to be not the case anymore. It just seems to just emit them and magic happens and you, if you write to the bottom 16 bits, then you don't have to do any extra work. But yeah, but they're all 64 bits wide is my understanding. Yeah, good question. Okay, one over there. Do you want to try and pass it over rather than, excellent.
Do you have much of a sense of how much variety there is in the design between like these Intel CPUs and AMD or even like other high performance CPUs?
Not really, actually. No, my sort of childhood experience was all ARM, but then that was very, very old and not very sophisticated. And then I've only really been concentrating on the Intel CPUs. That having been said, the things that I know are different in AMD are the branch predictor. That's something I've done my own research onto, and that's got a very different ethos. It's sort of, but I don't know about these kinds of aspects of it. Maybe someone else in here will do, but no. Sorry for the non-answer. And there's a question there.
I've heard like two perspectives on whether ISA matters. Like, is ARM faster because of all the non-ISA things, or is it faster because of ISA? So, what is your take?
So I think again in those halcyon days when ARM was actually a RISC processor and was I could disassemble it by looking at the instruction because they were that straightforward. I think it probably had an edge against the contemporary x86 era. Thoughts, but I think that ship has sailed, with all of the new whiz-bang features that the ARM can do now. I think they have just as complicated a set of decode steps and prediction and pipelines and out of order and all that kind of stuff. So I don't know that it makes that much difference. It's more of an implementation detail of the front end as to how the actual adds and subtracts get their way into the ALU than there is, I guess the one argument could be that the x86 ISA is sort of a poor man's compression, so you get a little bit more iCache usage, maybe. But we've all seen 15-byte instructions as well. You're like, I'm not sure that's better, So yeah, no. Again, another non-answer for you there, I'm afraid. Question at the front, I think. If you want to carefully, here we are. Lovely.
Like, how did anyone figure any of this out? Like, what kind of crazy experiments are people running to figure all this out?
So yeah, huge shout out. So the OG for all this is Agner Fogg, who is a Danish, or retired now, as I found out last week, a retired Danish anthropologist, which is exactly the kind of person you'd imagine. He seems to be more of a social anthropologist than a technology-focused anthropologist, or was. And so this sort of, why? I'm doing something. So he did a whole bunch of experiments to reverse engineer things. Now, so the short answer for that is there are performance counters. Those performance counters have revealing names, even if Intel don't really want you to know what's going on. And you can use them and infer from their usage. So like my own research back on earlier was about answering the question, the XKCD with someone is wrong on the internet. And you're like, I gotta go. It was one of those. Someone made some sweeping statement about like backwards branches were always predicted taken. I'm like, really? Always? But what if you don't take it? What if it's a conditional branch that's backwards? Anyway, the long and the short of it is, yes, it is. Some unconditional ones are different from conditional ones, or whatever. But like the measurements were to do two things that were in the Intel documentation about early re-steers, and they don't tell you what this is. It's just like, oh yeah, the number of times the pipeline was re-steered early, and you're like, okay, and then late re-steer, and then some other thing. And if basically my inference, which was backed up by the evidence I got and the conclusions I drew, was, like I said in the beginning, you don't even know if there's a branch in a 16-byte block of memory, right? So the fetcher is just going the BPU and the fetcher are just going to go 16 bytes, 16 bytes, 16 bytes, 16 bytes. But as soon as a branch is detected really early, like in that decode stage, it can send a message to say, oh, well, whatever you're doing is probably wrong, because if you didn't tell me that I had to branch at this point, you should branch. And so that was an early re-steer. So it's like only 3 cycles of latency, and then suddenly you're already getting in the right. And so by playing around with that, plus by branching forwards and backwards and then timing it and then seeing how far apart instructions were, that's what those color pictures were, you can kind of infer some of the patterns of what's going on. And then for things like the much more complicated stuff, like the micro operations and stuff, there are counters of how many micro-ops have been executed by each stage of the pipeline. So you can run experiments where you're just kind of adding over and over and over again. You say like, oh yeah, the counts are going up from ports 0, 1, and 7. So those are the 3 that can do this operation, and so on and so forth. And then you build huge dependency chains, and then you try and do some things behind the back of those dependency chains, and then see which other counters go up. And like, oh, these things are where we hit the renamer, but it wasn't able to rename anymore because like it was waiting. Things like that. So there's a whole bunch of experiments, and Travis Downs has probably got the best set of work on this. So this is his blog, but he also writes something called UArchBench, I'm getting that right, which is kind of like a whole suite of microarchitectural benchmarks. Agnafog has his own stuff as well. I've got my own branch of that, which is what I use for the BTB stuff, which I've made it recompile again. It was broken as hell. So yeah, and then Andreas Abel and his, I can't think of the other person on his paper, but I think it was his master's thesis, they spent a whole bunch of time trying to work out the algorithms behind the renamer and the which ports get allocated at what time and how long they are. And they found a whole bunch of things that like no one else had ever noticed before, which was just bonkers. And I love the fact that we can experiment with something which like I'm carrying around with me all the time. And you're like, I wonder how it works. And like, you can go and find out. But yes, so the short answer is all those weird counters and then very careful timings. And the sadness about this is, and I'm sure we talked about this earlier, is that most of these things only work if you have actually got a physical machine in front of you, which obviously I do in the case of a laptop and I do in my desktop at home. I tried to get a Granite Rapids machine, and it's expensive enough to hire them, and then I get to my Amazon account and I've got it running and I'm like sudo this and it's like, oh, there's only 3 hardware counters on this. I'm like, I'm sure there's more than 3 hardware counters. Oh, it's virtual, isn't it? Ah! So I couldn't do the measurements I wanted to on those. And it's the same with Magic Trace, right? You need a real, actual, honest-to-goodness computer to run it on in order to actually get an answer. Any other questions? Thank you, by the way. You've got one next to you and then we've got one behind you.
Do you have a favorite x86 instruction?
Do I have? Oh, no. I'm very simple, actually. I quite like, there's one of the parallel comparison things that I always forget, but when I see it, it makes me chuckle, and I can't think which one it is. It's like PCL MEQ something. No, yeah, good question, and it's the kind of thing I should have a good answer for, but I do not know.
We'll accept least favorite, too.
Least favorite. Least favorite. I mean, no, I wish I had a pithy and amusing answer for you, but it put me on the spot. They took one away for the, they took one instruction away that used to be used for binary coded decimal, and they didn't bother porting it to the 64-bit. And I'm like, come on, you have so much legacy crap, and you didn't bring this instruction over, and that's got a funny name. I can't remember what it is now, but anyway. Yes, sir.
Presumably, we can use this to make our code fast, and Intel wants their CPUs to look very fast. So why is this all so hidden and impossible to describe, and why don't they just tell us more? I
don't know. So you can, again, it may be possible that within this building there are people who have access to information that I do not have access to, but I was certainly aware of at my time at Google that if you have a certain volume of chips that you buy from Intel, then there's a sort of sliding scale of how friendly they'll be with you, going from like, we can send somebody to come and help you debug your problems through to we can fabricate your own specification of chip, and here's the designs. They had the pink books, I think, and the yellow books. They were like different names for different levels of classified information. And certainly, when I had some very off-the-record conversations with some contemporaries around the Spectrum meltdown times, they were like, well, yeah, the pink thing, it talks about it. And I'm like, what do you talk, whoa, what? And they're like, have you not got those? I'm like, no. And they're like, oh, we shouldn't have said anything. I'm like, oh my God, even knowing that they exist. So I think some people do have access to this information. But to answer your actual question, I think they don't want to promise things about how it works because, what is it, Hiram's law, anything that can be relied upon will ultimately end up being relied upon. And of course, that's why we have instructions from the 1970s, although not my friend, the binary coded decimal adjustment. So they don't want to be painting themselves into a corner, and presumably as well as an intellectual property aspect to this, even though it gets reverse engineered. So like the branch predictor in particular, I think is one thing, because I do know that AMD is very different from the x86 one, sorry, the Intel one. And yeah, the folks who reverse engineered the Skylake branch predictor, they found a really interesting case where, and again, I was going to do some more slides that I could flick to, but unfortunately I didn't get around to them. But effectively, the various smooshing and hashing and things that it does to kind of come up with this is a fingerprint for this particular branch and the sequence of operations that led to it, such that I can have a table that says, hey, the last time we were in this state at this branch, we took the branch, that kind of feel. That's what's going on in a branch predictor, right? They discovered, these researchers, that the bit 5 of the branch address was essentially a direct map. So if it was clear, there was one half of the entire branch prediction system that you were using, and if it was set, there was the other half of the entire, effectively the hash didn't mix bit 5. And they used it to generate a sandbox, sort of meltdown Spectre style, where if you're a JIT compiler, you could contrive the code that you JIT compiled to only allow branches to happen when bit 5 was set, right, in the code that you generated, and then you make sure that your supervisor and all the checks about, like, are you in bounds, are you not in bounds, whatever, has people laughing, bit 5 clear, and now you effectively have 2 branch prediction domains, and now you're not subject to Spectre and Meltdown. How cool is that? And I'm like, yeah, if they'd have told us that, we'd have used it. But then, of course, now they'd be like, oh, shit, we have to keep it this way. We probably didn't even know ourselves that bit 5 was leaking out like that. So I think it's a bit of, what is the Hanlon's raisin? Never ascribe, no. I don't think Hanlon's raisin applies here, which is the never ascribe to malice, which is explained by incompetence. But no, because I think they're very, very common to people. I think some very careful decisions have to be made about this kind of stuff. I mean, we're obviously in a very sensitive intellectual property environment ourselves. And so, trying to toe the line between the things that we do think is useful and the things that most people don't need to know but could be a competitive advantage would be my biggest guess there. Plus, just documenting it would be a pain. Any more questions? Okay, I'm being waved at from the back, as in times like we're done on the time. So once again, thank you all for inviting me out here. I've had a wonderful time. And yeah.